Dr. Colbreth here with problem 37 from chapter 16. It says 2 loudspeakers emit waves along the x-axis. The sound has a maximum intensity when the speakers are 20 centimeters apart. The sound intensity decreases as the distance between the speakers increases, reaching 0 at a separation of 30 centimeters. What is the wavelength of the sound? Is part A, and part B says if the distance between the speakers continues to increase, at what separation distance will the sound intensity again be a maximum? All right, so we're given 2 pieces of information in this problem. One, that we have a maximum intensity when the path length difference is equal to 20 centimeters, and we have a minimum intensity when the path length difference is equal to 30 centimeters. So we can say that the path length difference, delta R, in scenario 1 is equal to some multiple of the wavelength times lambda. We don't know how many cycles it's passed, but we know that it has been an integer number of cycles. And then as we continue to separate them, the second scenario tells us that the path length difference in scenario 2 is going to be that same m, but we've gone half a cycle more, all times the wavelength lambda. And so what I'm going to do now is I want to get rid of these m's, so I'm going to take expression 2 and subtract expression 1. So if we get delta R2, the path length difference in scenario 2, minus the path length difference in scenario 1 is going to be equal to the difference of the right-hand sides of these problems. So that's m plus a half times lambda minus m times lambda. I'll write the whole thing out to be explicit. And if we combine these factors of lambda, we're going to find that the m's cancel. And so we have to get delta, the path length difference in situation 2 minus the path length difference in situation 1. Well, that must be exactly half of a lambda, or lambda over 2. And so now we can plug in some numbers, or actually I'm going to move the 2 to the other side. Lambda explicitly is equal to twice the difference in the path lengths between scenario 1 and scenario 2. So this is the path length difference in scenario 2 minus the path length difference in scenario 1. That is equal, twice that is what is going to give us the wavelength lambda. So that means that 2 times 30 centimeters minus 20 centimeters is equal to lambda. 30 minus 20 is 10, so that means our wavelength must be 20 centimeters. So that is the answer to part A. Now part B says if the distance between the speakers continues to increase, at what separation distance will the sound intensity again be a maximum? Now we know the wavelength is 20 centimeters, and we know that we had a minimum intensity at 30 centimeters of path length difference. So that means that 30 centimeters we can see is actually 1.5 wavelengths for our path length difference. The speakers are separated by more than a full cycle, but less than 2. At 30 centimeters, that's 1.5 cycles that separates the speakers, meaning that the path length difference between one speaker and the other, which reaches the point of the observer, differs by 30 centimeters in this case. So we want to talk about when the path length difference is going to equal an integer number of cycles. Well, the next integer number of cycles is going to be 2 lambda, or 40 centimeters. So as we go from 30 centimeters to 40 centimeters, we're once again going to find a maximum value. So in part B, the next maximum is when the path length difference is equal to 40 centimeters, which is equal to 2 lambda.